Hello guys, welcome back to my channel. Mason African Motives. Still working on engineering science and 4. So like we requested guys, for the question paper which was written in July 2022, so we have it, and we're going to work on it. So we have the question paper, and it's actually a 3-hour paper with the instructions. I think it's very clear. It's all about to read the instructions properly there, and also what is important, everything, the calculations and the formulas, everything must be clearly done in a proper way. All right, so anyways, that's it guys from this part that we are having, and we shall just quickly rush through the questions. Then on number 1 we have a question which is on kinematics, where we are given that a bus and a truck leaves simultaneously from a flock in a road. Okay, so the truck travels northeast at a velocity of 85 kilometers per hour, and the bus travels east. This is directly east. Take note guys, this is directly to the east and at 104 kilometers per hour. So these are the velocities actually. So calculate the velocity of the truck relative to the velocity of the bus, and that was actually 4 marks. Okay, so let's just make a sketch of what is happening here. So we have got something like this. Actually, let's just see, this is 1.1. Let's just make our plane maybe just like this, so that we can have our diagram here, and I'll just show you what is happening here. All right, so actually here I just used these continuous lines, but I was just supposed maybe here to use some of the broken lines. Anyways, it's fine. So we know that this is our north guys. You must remember this is your east, this is your west, and this is your south. So the truck is traveling northeast, which means it's between north and east at a velocity of 85. So between north and east, so this is in between. So it is going to divide this quadrant into 2 equal parts. So this section will be divided into 2 equal parts. So this is your 85 kilometers per hour. This is for the bus, and this is for the truck, and the bus is the one which is directly to the east, which means it is in this east line. Take note guys, directly to the east, which means is to the east, which is 104 kilometers per hour. So this is 104 kilometers per hour. But I said, so let's just make this is our A and this is our B. So like I said guys, this is directly to the this is between north and east, so it is going to divide. Remember, this is 90 degrees, so it is going to divide into 2, which is 45 degrees, and also here 45 degrees. So which means from east to north it's 45 degrees, from north to east it's 45 degrees again. All right, so what I'm going to do so that I can be able to calculate this resultant, I'm going to just reflect. So remember, we can reflect this into that side. So actually this was supposed to be something like this in a broken line. Then we transpose it, or we reflect it to this side. So we shall have this velocity of 104 now this way, which is 104 kilometers per hour, like that. So that's what you're going to have. And also since we can create a parallelogram. Remember, I want to create a parallelogram here, so we shall have something like this. This one is going to be parallel to this side. Sorry for that, let me just continue with it. So it is going to be parallel to this side, and also this side will be parallel to this side. So it is going to be also parallel to this side, but it's only because my sketch guys is not that nice, but that is what I'm trying to say. So this will be this direction, and this 85 is the one that is the same as this one. So this is your 85 kilometers per hour. So this will be our resultant from our here. This will be our resultant here, which is the one that we want to calculate the velocity. Then the angle that we shall take is the angle that is in between these two, the horizontal and the resultant. So which means we are talking of this angle to be our direction, which is our theta. Or we can take this angle between the north going to the west, this one, which can be our alpha. So let's just call this angle alpha. So which means our resultants, I mean the directions can be two answers. This one, you can take this one, which is from the west to the north, which is west theta degrees to the north. Or you can take this one from the north going to the west, which is going to be north alpha degrees going to the west. So that will be our answer. So now let's calculate the resultant. So as we can see, also the other thing, this is a parallelogram, which means these lines, they are parallel. So this angle here and this angle here will be equal. From your corresponding angles, remember from your mathematics, if these two lines are parallel, then these two angles are equal. So this will be 45 also. So what can we do to calculate this resultant? As you can see, we are given two sides, this side and this side. So we can calculate the third side using cosine rule. Remember, cosine rule can give us that, because cosine rule states that a squared is equal to b squared. But as we are calculating r in this case, we are going to have r squared is equal to the square root of b squared plus c squared minus 2bc cos a, which is cos the angle that you are given. If this is a, then it is going to be cos a. So in this case, we are calculating r, so it's going to be cos r. So let's just put it as cos r like that, or we can just leave it as a. Okay, no problem. But remember, guys, that your B and your C are the sides that you're given, which make the angle of 45 degrees. So you've got 104 and 85. So I don't know which one are you going to start with, but the answer is just going to be the same. So in this case, I'm going to have it as 85 squared plus the other side is 104, like I said. So it's going to be 104, not 140, but 104 squared minus 2 times B and C, which is 85 times 104, like that. So you're just repeating this B and C here. Cos A, which is cos the angle that is in between the sides, and in this case, the angle in between the sides is this one, which is 45 degrees. So we shall have it as cos 45 degrees, like that. So that's it, guys. So which means simplifying this from a calculator, you shall have your r and round off to 3. So this is r, not r squared, because we have already put the square root. So this is going to be r like that. If it is r squared, then the moment you put the square root, it will be r. Okay, take note there, guys. So you shall have 74, 4268, something like that, which is going to be 427. So this will be 427, and this is velocity in kilometers per hour. So that's what we are having there, guys, from our velocity, which is the resultant. So that is our part that we are having, and we need to calculate the direction now, which is this theta here. So take note, we now have this r here, this resultant, we now have it, it's 74,427. So that can help us to calculate this theta, because we've got this angle which corresponds with this side, this angle which corresponds with this side. So we can apply our sine rule. Remember that our sine rule states that sine A over A is equal to sine B over B, which is equal to sine C over C, something like that. So which means we can apply our sine rule because we are given that condition. So it is going to be sine A over A, which is equal to sine B over B, equivalent to sine C over C. But here we're just working with two things. So we want to calculate theta, so we are going to use as sine theta over the corresponding side. So take note, it's angle versus corresponding side. So it's sine theta over its corresponding side, which is theta corresponds to 85, which is equal to sine b over b, so we need a condition or like this one which corresponds to this one. So we can't use this 1/4. Why? Because this side does not have a corresponding angle here, so it is going to be difficult for us. So that is why we are taking this angle and this side that we calculated. So it is going to be sine 45 degrees over this side that we calculated, which is 74.427. That's 427, like that. Okay, so since we want to calculate the angle theta, let's play around with this calculation. Multiply by 85 to remove this 85 here, so which means you're remaining with sine theta. So remember, to find theta, it is going to be arc sine like this, which is shift sine. So it's just arc sine of this. So we multiply 85 times sine 45, which is 85 sine 45 degrees, like this. So this will be in a bracket from your calculator, everything over 74.427. So that's what we have. And arc sine, that is going to give us 53. So therefore our theta is going to be 53.879, whatever that you have, which is 8578, which is 858. So this will be 858 degrees. So that is our angle theta there. So like I said, if we are to take theta, therefore our direction is going to be west, theta degrees to the north. We are using this theta, not alpha, because we calculated theta, we didn't calculate this alpha. So we're going to take this as our direction, which is going to be west, the angle theta degrees to the north. So our theta in this case is 53.858 degrees to the north. So that is what we have in this case as our resultant, or as the direction. So which means therefore the velocities that we are given, the relative velocity is going to be A, which is equivalent to we calculated the resultant. Remember, our resultant was 74.427. That was our resultant kilometers per hour at this direction of west, 53.858 degrees to the north. So this will be our answer there. So that is what we had in this condition. So it's, as you can see, it's all about the diagram. It's all about the diagram. If you have got drawn a diagram in a proper way, then everything is going to be clear, just like that. Then you're given an aeroplane flies to its destination, which is 300 kilometers directly east. So this is directly to the east of its starting point. The pilot wants to complete the flight in 50 minutes. That is the time. All right. There is a southwesterly wind blowing at 10 meters per second actually. Calculate the velocity of the aeroplane and the direction of the flight. So take note, guys, here we are talking about velocity. We are given the velocity of the wind, but here let's talk about the aeroplane. On the aeroplane, we are given the distance and the time that it's supposed to take. So which means we can work out the velocity there of the plane, because we do not have this velocity. Okay, so that's the first thing that you're supposed to do in this case. So remember that velocity is equivalent to the displacement, or the distance over the time that is taken, and this must be in meters and this one must be in seconds, so that we can obtain meters per second. All right, so therefore our velocity, which is the velocity of the aeroplane in this case, is 300 kilometers, which is the distance or the displacement. So 300 kilometers, guys, this must be in meters, so we multiply by 1000, which is 300 times 1000. That's to convert to meters. So it is now in meters over our time in this case is 50 minutes, so this must be in seconds. So you know that in a minute we've got 60 seconds, so you have to multiply 50 by 60 so that it can be in seconds. So this is now meters per second. So as you can see, guys, this is just something like 300,000 over 3,000. This is what is happening here. So our answer is going to be 100 meters per second. So this is the velocity that the aeroplane was moving at. But now this is not what we are talking about. We are talking about before there was a wind which was then blown of 10 meters, which is blowing of 10 meters per second southwesterly. All right, so this is southwesterly wind that was blowing. So we have got something like this. That is what you're going to have. So guys, this is all about your diagram. I always tell you guys that it's all about your diagram, and also these diagrams might be different. Like the first one that we did, we could have done it with so many methods. So with time I shall work out all those methods so that you can be able to understand, because someone might be surprised about the methods that I'm using. There are so many methods actually. Calculate the velocity. Okay, so we said there is a southwesterly wind that is blowing, but let's start with the aeroplane, which is, we calculate the velocity of the aeroplane. We said it's 100 meters per second, but where is it going? It's going directly to the east, just like what we had here of the bus, which was traveling directly to the east. So this is going to be here direct to the east like this, which is 100 meters per second. So this is our 100 meters per second, the one that we calculated for what, for the aeroplane before there was this wind, which was what, which was blowing before. I'm not seeing the paper where I wrote it, but that is what we obtained. I still remember this. Now there is a wind which is blowing southwesterly at 10 meters. So southwest, remember guys, this is our east, this is our north, our west, and our south. So southwesterly, which means it's in between south and west. So the wind is blowing. All right, this is our wind which is blowing southwest, which means we have got 45 degrees. It is going to divide, but the aeroplane is here, so which means this wind is going to affect this way. It is going to be like this. Now the wind is affecting the aeroplane. All right, so this is what we have now for the wind, which is our 10 meters per second, and this angle, as you can see, it's 45, so this one also is going to be 45 degrees here. All right, so that is what we have. We extend the wind there, so which means our diagram can be further on be given like this. We can have our diagram. Now we have to calculate between this is the wind here and this is our aeroplane. So now this will be the resultant that we have to calculate, which is the velocity that is going to be there. Is that so? Yes, that will be something like this. So that's going to be the velocity of what? Of the aeroplane here. Okay, then, so like I said, depends with the method that you're going to use, because you could have use another way or another diagram actually. All right, but can we calculate this VA? Yes, we can, because we have got that same condition that we had last time. Remember cosine rule again, because we have got two sides and an angle in between. So we are back to that cosine rule. So you see guys, this is just a repetition. That is, we are having just a repetition. So our VA is going to be the square root of which is the velocity of what? Of the aeroplane. All right, that is the velocity of the aeroplane, this one. So we said our formula is a squared plus b squared. Actually, it depends if you start with a, so we're gonna use, let's use b squared plus c squared minus 2bc cos a, so that I don't confuse you to the one that you are used to. All right, so this is our formula there, guys. So what we are going to do is to make substitutions there. remember our B and C simply means the sides that are creating the angle, which is 10 and 100. So we've got 100 here and 10 and an angle 45. So it's the square root of 100 squared plus 10 squared minus 2 times 100 times 10 cosine of what? Of the angle that is in between, which is 45 degrees, like that. All right. So from your calculator, you're going to obtain 93,175, whatever that we have, which is going to give us 93,178, because that 5 is going to change 7 into 8. So it will be 198 now meters per second, because remember we calculated this as meters per second. So that is it, guys. And we need to find the resultant now. So what is going to be the resultant that we need in this case? Because as we can see that we need an angle there. Okay, so which one is going to be the angle that we are having? So we are going to take this, because this angle theta. So remember our VA, we just calculated it now, and our VA, we obtained this as 93,198 meters per second. All right, so that means in order for us to calculate this theta, just like what we did from the previous diagram, guys, this angle corresponds with this side and this angle corresponds with this side. So you can apply sine rule, sine theta over 10, just like what we did from the previous case. So sine theta over 10 is equal to sine what this time? Sine 45 over this one. So guys, as you can see, this is a mere repetition. You'll be in exam and you'll be surprised, am I answering the same question or what is happening? But that's it anyways. So let's find our theta there. So multiply by 10 to remove this 10, just like previous part. So we shall have our sine theta as this part. So which means to find theta, it is going to be arc sine. So this arc sine, simply shift sine from your calculator. So it's 10 over, so it's 10 times sine 45, which is 10 sine 45 degrees over 93,198, like that. So you just close this bracket. So this actually on your calculator, sine 45 will be in a bracket, you know that. So it's sine 45 degrees, something like that. So this is going to give us 4,35129, which is 51 in degrees. So this is our theta in degrees. So therefore, as we can say, the velocity of the aeroplane that you're given, that is the aeroplane here, is 93.198. Okay, let me just try and adjust 93.198 meters per second, and the direction now. So take note the velocity and also the direction. What will be the direction? So we are going to have this from the east, which is east 4,351 degrees, going to the south. So it's just opposite the one west, south, west, south, now east to the south. Okay, so that's what we had from this particular question. So I don't know, guys, how you answered this question, but like I said, we have many methods, so I'm gonna come back again with other methods, but they must give us the same answer anyways. Then a bullet is fired at an angle of 33 degrees to the horizontal at a velocity of 410 meters per second. Calculate the maximum. So actually on projectiles, we know that this one is all about the formulas. If you are using the current textbooks for science, you see that they made nice formulas there that you just need to substitute on your formula, even without the diagram, even without anything. You can just see what is actually happening from there. So you know that that's our projectile there, that's our hue, which is okay, let me bring it 410. We've got 410 and angle of 33, so we've got 410 meters per second and angle of what? Of 33 degrees. So remember, this is your horizontal distance, vertical distance. All right, so the question is to calculate the maximum height reached by the bullet. So the maximum height reached by the bullet, which means you are talking about a vertical, because the bullet is going to be like this. So this, we are talking about a vertical distance, and that vertical distance, which is our SV, was the vertical. I'm just going to use it as S vertical max or SY max, or just S max, like that. So, but that's it. So from our formula, like I said, from that textbook, guys, is directly given. The formula is going to be U squared sine theta squared over 2g. So you can use this formula. So this sine theta squared, this one, if I write like sine theta squared from your calculator, you put it this way, sine theta, then you square the bracket outside. That is what it means. All right, so let's substitute our u, which is the velocity, 410 squared sine theta squared, which is this one that I said you're going to write it like this. So it's sine 33 degrees, then you square everything. So you open the bracket. So on your calculator, it shall be like this. Remember, when you put sine on your calculator, there's a small bracket that is going to open. So that is what your calculator must be. This is what you're supposed to have on your calculator. All right, over 2 times g, which is 9,8. It's just like that. So this will give us 254. Yeah, that's 2544,0706. So that 6 gonna change that 0 into 1. So that's our answer there. So that's what we had, guys, on 1.31, the maximum height. Then the horizontal displacement. All right, sorry for that. So now we want the horizontal displacement when the bullet hits the ground. So this is the horizontal displacement. So like I said, from a formula, your S horizontal, which is SH, which is H horizontal, will be equal to U squared sine 2 theta over G. So it's a matter of memorizing the formulas, but it's nothing, guys, to memorize these formulas, especially towards exam. With that exam pressure, you must do that. All right, so U squared, which is our 410 squared times sine 2 theta. So this is sine 2 times our theta. Remember, our theta is 33 degrees, so it's 33 degrees. So on your calculator, you shall open a bracket like this, and don't put this, just 2 times 33 over g. We know that our g is 9,8, just like that, guys. So you see, knowing formulas, it helps you a lot. You don't sweat in exam trying to figure out what am I doing there. It's just substituting, and you obtain this answer, 1017, which is 101, because this is gonna be, and this will be in meters. So that is our horizontal displacement. That's what we had. And we move on to the question, which is on dynamics, where we are given that the effective diameter on the wheel thread. So we are given a diameter on the wheel thread, which is a cutter, which is 405 millimeters. So actually, when you are given diameter, guys, you do not know how you are going to use it, but what you need is to leave your answer in meters. So remember, 1 meter is 1000 millimeters, so divide by 1000, that's gonna be 0.45 meters. Also, you do not know whether you're going to use diameter or you're going to use radius, so just find your radius. Also, you never know what is going to happen, so divide by 2, which is going to be 0.2025 meters. I don't know. That's it. So I don't know what you're obtaining from your calculator. That's what I'm obtaining. Then calculate the following. That's what we just have. Calculate the following on 2.1. The distance that a point on a thread of the tire will cover if the tire does 1 revolution. Take note, guys. We are talking of distance when 1 revolution was made. Okay. So we know that in a revolution, in 1 revolution, we have got 2 pi radians, because we are talking of what? of 360 degrees, but in radians that's 2 pi, because this is our angular displacement, which is 2 pi radians. That is our angular displacement. So the question is to calculate the distance, not the angular displacement, but the distance. So which means we are talking of what? Of s. So remember the relationship between linear motion and angular, that s is equivalent to r theta. If you multiply times radius, you are now into linear. So your radius is there. Just take your radius, 0.2025 times theta in radians, which is 2 pi. All right, so this is going to give us 1,27234, like that, which is 272. That is our distance in what? In meters. So this will be linear, so it will be meters, angular in radians. Okay, then the angular displacement of a point on the thread of tire after 10 revolutions. So take note, angular displacement, which means we are talking about what? About theta. Okay, so this one is theta, where we know that so like how we say that in a revolution we have got 2 pi radians. So how many revolutions we have this time? We have got 10 revolutions. So we simply multiply 2 pi times what? Times 10. That will be our theta in radians, which is going to be 20 pi rad. So that is our theta, our angular displacement. Angular displacement is measured in radians. All right. Then the angular velocity of a point on a thread on the wire when the car is traveling at 110 kilometers per hour. Okay, so the first thing that you're supposed to ask yourself is that what is represented by 100 kilometers per hour? Yes, we are calculating the angular velocity, which is omega. So this is omega, this one, that is your angular velocity. But what about this 100? What does it represent? This is kilometers per hour, which means you're talking about what? About linear velocity here. So this is your linear velocity, which is your v. So this v must be in meters per second so that it can help us to calculate r, because we know that v is equal to r omega, like this. So we can play around with omega and make it the subject, so that our omega is going to be, you divide by r here, which is v over r. But this v must be in meters per second, so we have to convert 100 kilometers per hour into meters per second, which is divided by 3,6, and that's gonna be 27,777, like that, which is 27,778. All right, so that's our linear velocity in meters per second. So we shall have 27,778 in meters per second over the radius. Remember the radius, we said it's 0. From this part here, 0.2025, 0.2025. So this will be our omega, which is our angular velocity, which is measured in what? In rad per second. All right, so that's it, guys. So which is going to be 137,1753. So it's going to be 175. That will be in rad per second. So that's our angular velocity, which is this omega. So omega is equal to 137,175 rad per second. So this is angular velocity. This is linear velocity, which is measured in meters per second. So the relationship is that from linear to angular, you multiply by from linear to angular divide, but from angular to linear you multiply by r. So that is your relationship, just the one that I wrote. Then you manipulate that formula. Okay, the angular retardation, so you have to calculate now the angular retardation, which means you're talking about what? About alpha. So alpha, that is the one that represents our angular retardation, just like angular, just like deceleration, but this one it's angular, which is our alpha, but this is a deceleration that is occurring. If the vehicle is brought to rest, from which velocity? Now, okay, with a uniform reduction speed from 100 kilometers per hour in 25 seconds. All right, so this is it, guys. In 100, from this speed of 100 kilometers per hour, this is a linear velocity, but we are talking about angular deceleration, which is angular retardation. So we can't use this 100 kilometers per hour because this is for linear. We have to use angular velocity, which is equivalent to 100 kilometers per hour, which is our angular velocity. The one that we calculated, it was 137,175 rad per second. All right, so that is our initial, this one. Then our final is when it is brought to rest from, which means that is our initial, then to rest, which is at 0. So this one will be at 0 rad per second. All right, what else do we have? We have given the time of this reduction in 25 seconds. So we've got a time of 25 seconds. So remember that alpha is simply the change in what? In angular velocity over the time. So our alpha is going to be omega 2 minus omega 1 over t. That is what we have. So omega 2, that's 0, minus omega 1, which is 137,175 over the time which was taken, which is 25. So that will be our angular retardation, which is going to be a negative 5,487. Yeah, that's rad per square second. So remember, retardation or deceleration in terms of angular is measured in rad per square second, but this one is a negative because it's a reduction that is occurring. If it was an increase, therefore it was going to be angular acceleration, but this one, it's a reduction, that is retardation, deceleration. Okay, on 3.1 we are now asked to define the term potential energy. All right, so potential energy, as we know, guys, that we are talking about the energy that just a body possesses on its state of what position, where it is located at that point. But this is going to be because of its position with respect to the reference of what? Of the plane and gravity. That is potential energy, and we know that energy is measured in what? Energy is measured in joules, as we know, guys. Okay, so anyways, that was it. Then we are given that on 3.2, a cyclist with a mass of 120 kgs accelerates uniformly from rest up a gradient of 1 in 35 and reaches a speed of 65 kilometers per hour after 2 minutes. All right, so let's just have something about this information before we attempt the question there. So it's this one, there's a gradient, which means this one we are talking about what? An inclined plane of a gradient in 1. So you can actually have our theta there. So all you need is to list down your information, which is the data there. So you've got the mass of 120 kgs. All right, so let's start with that. Our mass in this case is 120 kgs. That is from our object here. Then it accelerates uniformly from rest, which means from rest, that is at our initial velocity from this, which is 0 meters per second, up a gradient of 1 in what? In 35. So this gradient, what does it mean? Theta will be arctan 1 over 35, so that we can obtain the angle there, which is arctan 1 over 35 is going to give us something like 1,63536, which is 1,637 degrees. That's our theta there. So which means we have got 1,637 here degrees. Okay, anyways, let's move on. So here, sorry, I'm now taking from another question. And reaches a speed of 65 kilometers per hour after 2 minutes. So we've got the final velocity, we have initial, now the final velocity of 65 kilometers per hour. So we have to divide by 3,6 so that it will be in meters per second, and this will be our final velocity, which is 18,056, something like that, which is in meters per second now. So we've got 18,056 meters per second, and what else? We've got the time after 2 minutes. So this is your time in which is supposed to be in seconds. So we multiply by 60 because we know that time in a minute we've got 60 seconds. So this will be 120 seconds. So that's our time here in seconds. All right, so that's it. So the question now, we are listed the data that we are given, we have taken it down. Now let's have our question. The question is now to calculate the acceleration of the bicycle, and we've got 3 marks just to calculate the acceleration of the bicycle. So acceleration, we can actually use the information on linear motion because we've got we've got final velocity, and we've got time. So which means we can actually play around this question here. So we can play around this one. So we know that v is equal to u plus 80. So that will be our acceleration there. V minus u over, we divide by t, which is going to be your a. So our a is going to be v, which is our final 18.056 minus the initial velocity here, which is 0. So we've got 0 over the time, which is 120 seconds. All right, so that's it, guys. So using calculator properly, we're going to obtain 0,15, that's 0,1504. Okay, that 4 cannot change, so it's going to be 0 here, which is just even 15, and that is acceleration, which is measured in meters per square second. All right, so that's it, guys, from this diagram or from this information. I think information was just direct. Then the kinetic energy that the bicycle possesses after 2 minutes, what is going to be our kinetic energy after 2 minutes? And we are referring to the time frame of 2 minutes, which means to the same time that we had on this information, what is our kinetic energy after that? So as we know that kinetic energy actually is equivalent to half mv squared. Is that so, guys? Our kinetic energy, that's half mv squared. So we've got half times the mass, which is 120, multiplied by v squared, which is our velocity of 18.1 that we converted. Remember, we converted this to meters per second. All right, so this will give us something like 19561,14816, which is just gonna be 148 in joules, like that. So that is our kinetic energy. Yes, you can convert to kilo if you want, but I don't think there was need there. The gain in potential energy now, and this is actually 5 marks to make it 12 everything. So what is the gain in potential energy? Okay, so actually the gain in potential, we are talking about the potential energy that we shall have at the top. Remember, we started from here, then at the end will be at the top here. So this is where we are at the top. So after that, what do we have in all? Okay, our potential energy, it's mg, that is mgh, you know that. So it's going to be mgh, but because of the incline now, we cannot use this h as it is going to be by sine theta. So that is what we are going to have in this case. So this h here, it simply indicates, or it simply represents the distance which was traveled, which is actually the displacement in this case. So we have to find, if we are not given, then we have to find the displacement from this point to this point. All right, so if we have this displacement from this point, then we calculate now this part here, which is the one that we are saying it's s sine theta, which is h sine theta. All right, so Now that's what we need. So this displacement here is the one that we are referring to as our h. So we have to find the displacement. So where can we find this displacement, guys? Okay, we come back to our linear motion. Remember, we calculated acceleration, and we obtained an acceleration of 0,150. Still remember, 150 was what? Yes, that is what we obtained, meters per square second. So we can include this now to the linear motion there, so that we can calculate s first. Then we'll be able to substitute it here, because everything is there, but we do not have this. Remember, theta, we calculated it from that information of 1 in 35. So where are we going to have this? Well, we know that 2as is equivalent to v squared minus u squared. So since we want s divided by what? By 2a by 2a. So s is equivalent to v squared, which is 18.056. That's our v squared, 18.056 squared, minus u squared. Remember, our initial velocity was 0 squared, all over 2 times the acceleration, which is 0,150, which is just 0,15, like that. All right, so this is what we have. We play around with our calculator, so we are going to have something like 108.7304, which is 7304, which is just a 0 there in meters. So this is our s, which is the one that we are referring to as what? As h. So therefore our potential energy, like we say, that it's mgh sine theta. We shall need to substitute the mass and everything. So remember, our mass was 120 kgs here. So we've got 120 times g, which is 9,8 times the h, the one that we calculated here, which is our s, this one. So it's 1086,73 times sine theta, which is the angle. So, and we calculated that when we were taking information. So you see, it's an advantage, because we are just substituting our theta obtained from arctan, which gave us 1,637 degrees. All right, so that's it, guys. We can obtain our potential energy from there, which is going to be 36,508,6 again 4. This is in joules. So yes, you can convert to kilojoules if you want, but that was it. That was our answer there. So I don't know, so many ways actually to do that. And on question number 4, define the law of moments. So the law of moments is all about that the clockwise moments should be equal to the sum of what? Of the anti-clockwise, provided that you are taking those moments about the same turning point, or the same what? Or the same fulcrum. That is what you must actually understand from that. Anyways, that is what we have for the law of moments. Then on 4.2, we are given, shown below is a simply supported light beam, which is ABCD. All right, on 4.21, we're asked to calculate the reaction forces at the support A and B and test your answer. Okay, so we need the reaction forces here, which is this A and B with the supports. All right, so anyways, this one is direct. Let's just quickly, we have this question, which is 4.21. So we shall take, I'm going to start with A, taking moments about A, then moments about B, like that, about D. So let's start with A. So we've got moments about A, taking moments about A. So if we are to take our moments about A here, guys, as we can see from this point A, this D is gonna go to A in this way, which is actually in an anti-clockwise direction. All right, so since I'm referring to that, so I'm going to take to that. So anti-clockwise moments, the sum of them will be equal to the sum of the clockwise moments. That is D going back to A is going to be 2 plus 2 plus 2, which is 6. So it's D times 6, which is 6D. All right. Now, do we have any that is on the anti-clockwise? This one we cannot say it's on the anti-clockwise because we don't know it's going this way or it's going this way, but it's at a point, so this one is going to be multiplied by 0, which means we are not going to take it because it's on the support, so we're not going to take it. We are going to move on to the other part, which is the clockwise. So do we have anything on the clockwise from A here? This is our A. As you can see, B is moving this way, which is the clockwise, clock like this, so it's clockwise also with C. So it's 30 times 2, that's 30 by 2 there. 30 times 2 plus, we move on to 40 times 4, back to A is 2 plus 2, which is 4, so it's 40 times 4. This one was a little bit direct, so anyways, that's our 6D there, which is going to be, you combine everything, which is going to give you 220 in this case. So divided by 6, our D is going to be equivalent, you're going to obtain 36,6666 like that, which is going to be 36,667. That's kilonewton there. All right, so that's our D. So which means we have this D, which is 36,667 kilonewton there. Now we move on to the other part, which is from D now. So we are going to take our moments about D. So we have moments about D, taking moments about D. Now from DA here is going this way, going to D, which is clockwise because it's going like this, which is clockwise. So we shall refer to the clockwise moments equal to the anti-clockwise moments this time. So that is it, guys. We are referring back to D. So as you can see, A back to D is simply having the same distance of what? Of 6 meters. So it's A times what? A times 6. So that's 6A. Do we have anything that is take note, guys, we are talking of what? Of D here. Do we have anything that is gonna go in the clockwise, in the anti-clockwise, I mean in the clockwise like this? We do not have anything that is going to go that way. So we are done. We move on to the anti-clockwise. So as you can see, this is moving this way, which is anti-clockwise, anti-clockwise again, and also 20 anti-clockwise. This time 20 we are going to consider it because it's not on D, so we are going to take it. So it is going to be 40 back to D. It's 40 times 2. That's 40 times 2 plus 30 times what? The distance is 30 times what? 30 times 4 plus 20 back to D, which is 20 times 6. So you add everything like that. So that 6A is equivalent to, combine everything, which is going to give us 320. Then you can divide by 6 there. So our A is going to be 53,3333 up to the end. So it's going to be 33, and this one cannot even change. So that's our A, which is 53,333 like that. So that's 53,333 kilonewton like that. So that's our A. Now they are saying, and test the answer. So you have to test the answer that the sum of the upward force should be equal to the sum of what? Of the downward force. That's what you're having, Newton's third law. So the upward force should be equal to the sum of the downward forces, which means upward, we're talking about what? About the supports A and D. These are the upward forces, which is 53,333 plus 36,667 should be equal to these ones. That's 40 plus 30 plus 20 there, which is 20 plus 30 plus 40. So this, if you add, will give us 90 kilonewton there, and this, if you add, will give us 90 kilonewton there. So definitely that's it, guys. That's it. So I hope it's fine. Then we move on to 4.2 to calculate the bending moments at point A, B, C, and D. Okay, so that's 4.22. And now on bending moments. So moment is force times distance, guys. All right. Anyways, let's see. So we need bending moment. So this is bending moment. We are going to start with bending moment at A. All right. So the bending moment at A, definitely we know that one is going to be a 0. That's our starting point. So that's one, it's a 0. All right. We move on to B. So we are going to have bending moments at B. So we're going to take, in this case, I'm going to take them from the left side. So from the left side of B, what do we have? We have got, remember, force times distance. So we've got this force times distance, and this is a positive. It's going up, so it's a positive. So it's 53,33 times 2 because it's a positive, minus this one, it's a negative because it's going down, so it's negative 20 times 2, back to what? Back to B. All right, so this is it, guys. We said 53,333 because it's going up, it's a positive, times a distance of 2 meters. But we are going to subtract because this A has got also 20, which is going down from the same point, so it's going to be minus 20 times the same distance of 2. Okay, so this is going to give us 66,666 like that, which is kilonewtons. So like I did, guys, with this one, we took them from what? From the left. We took them from the left side. Okay, let's move on to the bending moment at C. So applying the same concept, we could have done this, guys. You do the same now to see if you are taking this, is going to be this number times 4 minus 20 times 4 minus 30 times 2. But instead, guys, we can simply take it from the right because we just have one force here and a distance, so we shall take this, and it's a positive, it's going up, so it's just force times distance, so we can take it from the right in an easier way. So our force is 36,667 times 2. That's it, which is going to give us something like 73,334. That's what we have in kilonewtons, guys. So this one, we took it from what? From the right. All right, so it depends with the way, but you're going to obtain the same answer even if you take from the left. Then at D, we are back to the end there, the support. So this one is just going to be a 0 there, kilonewton. So that's what we had, guys, and that's what we're supposed to obtain. Anyways, then on 4.23, draw a bending moments diagram. Okay, so we need to draw a diagram that represents the bending moments. Okay, so this is what you're going to have now. Let's just put it this way. So here we are starting at point A. This is what we have at point A, the bending moment there. That's a 0 there, so this one is directly at 0 kilonewton. Then we move on to B, which is at this point, B and C and D. So this one we just take our 66. So this one is just a normal way, so we are just going to have a slanted line like this. We are not having any distributed load there, so it's just going to slant like this up to 66,6666 like that kilonewton. So this is our point A, this is our point B. All right, so from B we move upwards again. There's no distributed load, so we just move direct to 73 going upwards. So here we do not have any distributed load, so it's just going to be like this, but it's going up to a certain point there at 73,334 kilonewton like that, which is at point C. Then at D it now goes back to the ground now at D, which is at 0. So this now goes to the ground at D, which is something like this at D there, which is at 0 kilonewton. So this is our point D. So that's what we had on this 4.23, which is the bending moment diagram. So anyways, that's what we had. Then the further question now on 4.24 is to draw a shear force diagram. Okay, remember shear force diagram, guys. This is what is going to happen. I don't know if it is going to be clear on this space, but now because of the base that I'm having, I'm not going to have, but we are supposed to take it this way: A going down, B, C and D like that. But now because of the space that I'm having, it is not going to be clear, so I'm just going to put it on a separate diagram, but I hope you are going to understand what is happening here. All right, so this is the shear force diagram. Okay, so I want us to take note what is happening. Okay, let me just save our line so that I can explain with a diagram also. All right, so this is it here. Remember, when you are working with the shear force diagram, you have to consider the forces, the direction. Is it up or down? Okay, so let's start at A here, where it is 0. But there is a force which is our support, which is going up, and the point load which is going downward, this one. So now what can we do? Because we need a resultant from these two. So this is going up, this is going down from the same point. Okay, so which means we shall subtract this 20 because it's going down from 53,333. So 53,333 minus 20 there is going to give us something like 33,3333. So it will be 33,333. So which means this is going up to 33,3333. Guys, I don't know why I even wrote this here. I don't know. But anyways, sorry, let's just correct this. So this, like I said, is going upwards up to 33,33 from this point. So let's just say this is up to this point where we have got our 33,333 kilonewton, like that at this point. All right, sorry, I don't know. Let me just try and adjust this side so that maybe it can be clear. I don't know. All right, so but this is it, guys. That's our 33,33 like that. Okay, so I don't know what's happening here. All right, anyways, that's what we have. Then so we have to subtract, like I said here, the 2. Then we move a distance to B, which is going downwards. So there's a certain distance in between A and B of 2 meters. So that distance we just represent with a horizontal line. So you just draw your horizontal line just like this. So guys, take note about this part here. All right, so then we go downwards, but how many units are we going downwards? That's 30 kilonewton downwards. So it's 33,333, the one that we have, this one minus 30, so which is going to give us 3,3333. So this is going downwards up to 3, so 3. So take note, this is our 0 kilonewton here. So 3 is above the 0 there, so maybe it's somewhere here. So maybe somewhere here. That's where we have our 3,333 kilonewton. It's above the horizontal line. Then we are at B now. We move on to C. From B to C, there's a distance that is there. So we have to maintain a certain distance here. So we are going to maintain that distance of 3, so we are still at what? We are still at 3,333 kilonewton. That is where we are. We are still at that value. Then when we reached the point C, there's a point load going downwards of 40. So you have to subtract this, so it's minus 40. So 3,333 minus 40, which is going to give you minus 36, because it's like this, 3,333 minus 40, which is going to give us negative 36,667. So negative 36,667 kilonewton, it's a negative value, so it's supposed to be below the line. So, and also it's going direct down. This one, there's nothing, there's no distributed. So let's say it has gone down to minus 36,667 kilonewton, like that. Then what happened from that point C? From C, we moved a certain distance of 2 meters to D, which is a support, and we know that a support is a positive which goes upwards. So it moved a certain distance, right? That's a certain distance which was moved like this. Okay, still at minus 36,667 it now went upwards plus, because this is going up. So we're going to add 36,667. So as you can see, if you add plus 36,667, this one is going to give us a 0. So it is going back to the ground now at what? At 0 there. So that is what is going to happen. So because this is minus 36 is the same value here because it's on the same line. So that was your shear force diagram, but it must correspond with that bending moment diagram. Anyways, even if you separate it like that, it's still one and the same thing. Mark it in a proper way. All right, then we move on to question 5, where we had hydraulics there. Yeah, that is hydraulics, and we are given to state the characteristics of fluids, of liquids or fluids. So we have got fluids, we have got liquids. So there are so many characteristics. I don't know the ones that you got, but there are so many liquids. You know, they are virtually incompressible. They can retain the volume irrespective of what, of the shape of the container. All those. Then we also have fluids. They maintain some of the properties which are also similar to the liquids. So these ones, guys, we are not limited. So many answers that you can actually have there. Okay, anyways, we are given a water pump on 5.2 with a piston diameter of 42 centimeters and a stroke length 55 centimeters operates at this pressure. So that's just a simple pump that we are given. So let's try and list down the information from this water pump that we are given. So we are given the diameter 42 centimeters. Definitely we have to convert to meters, divide by 100, which is 0.42 meters. The same with the stroke length, which in this case I'm going to write as h divide, which is going to be 0.55 meters. Then we are given a pressure of 857 kilopascals. So that's 857 kilopascal, like that. And kilo means 1,000. So you just multiply by 1,000, which is 857,000 kilopascals, like that. Now it's now a pascal, not kilo, because you've multiplied by 1,000. So that's it. Then the question is to calculate here on 5.21 the volume of water delivered per stroke in cubic meters. What is going to be the volume delivered? So you know that volume is actually area times what? Times the height. That is from your mathematics there. So you know that volume is equivalent to area times the height. So the area, we are talking of what? Of pi d squared over 4 times the height, which is the stroke length. All right, so that's it, guys. So we can just make substitutions because we have our volume there. Our volume, that is pi d squared. Our diameter is there in meters. So pi times d squared, which is 0.42 squared over 4, multiplied by the height, which is the stroke length of 0.55. So definitely our volume is going to be in cubic meters from this part because we are working with meters. So our volume will be in cubic meters, which is going to give you 0.0761, something like that, which is 6 if you round off to 3 decimal places. So that's the volume, as we saw, guys. Okay, let's move on to another part, which is the on 5.22, which is the force exerted by the piston. What is the force? What's the relationship between pressure and force? We know that pressure is force over area. So if pressure is equivalent to force over area, which is measured in pascals, what about then pressure? Or what about then force? You can simply cross multiply because we need to calculate force. So 1 times F, that's F, which is equivalent to pressure times the area. So the pressure is there. Remember, we said our area is pi d squared over 4, which is this one that we have here. So area is there, and also pressure is there. Make sure that you use your pressure in pascals, not kilopascals. All right, so we're going to use 857,000 times the area, which is the one that we had here. This is our area here, so it's pi times 0.42 squared over 4. So that's what we have here. So that's it, guys. You substitute your values, which is going to give us something like 121.226, 2065. That's force in Newton. So you can actually give it to kilonewton, which is this point, which is 121.226 kilonewton. So that will be our force. So I don't know, guys, how you did it and what you think about the question and the presentation there, but that's what we had there. So we move on to another question, which is the work done per operation stroke. Work done, just 2 marks for that. So why? Because we know that work done is equivalent to the product of the pressure and the what and the volume. That's it, the pressure and the volume. So the pressure is there, which is 857 kilopascals, so it's gonna be 857. So I'm going to use this kilo. Kilo means 1,000, so I'm just going to use my kilo. So which means if I remain with kilo, my work done is going to be found in kilo. Okay, times the volume. Remember, we calculated the volume in this case, which is 0.76. So if you multiply these two numbers here, you are going to obtain 66.5, which is in kilojoules, like that. So that's your work done. Or you multiply by 1,000, you obtain that decimal, then you convert that decimal to kilojoules. Still your answer is the same. You are going to obtain the same answer there. Okay, so that's what we had, guys, on 5.23. Now we move on to 5.3, where we are asked to calculate the force exerted by a ram piston if an effort of 200 Newton there is applied to the lever of a hydraulic press. So there's a hydraulic press there, which is so take note, we have an effort which is applied, the mechanical advantage of the lever, which is 15. The efficiency of the press is 93%. Okay, we are given the efficiency, and we are given that the diameter of the plunger is 0.1 times of the diameter of the ram. All right, a lot of information. Anyways, let's just take it down. I hope it's gonna make sense. Remember, here I'm not talking of the topic. We shall talk of these topics, but I'm just applying what you're supposed to do there. So we are given the force, we are given actually the effort in this case, which is 200 Newton. All right, that's our effort in this case, which is 200 Newton here. Then we are given also the mechanical advantage of the lever, which is 15. All right, and the efficiency of 93%. Okay, so mechanical advantage, that is 15, efficiency, which is 93%. So 93%, or you can write as a decimal, which is 0.93. It depends with what you want. Then also you're given that the diameter of the plunger is 0.1 times the diameter of the ram. Okay, so I'm going to use D for the plunger and D for the ram. So they are saying that the diameter of the plunger in this case is equal to 0.1 times the diameter of what? Of the ram. So it's 0.1 D of the ram. So it's 0.1 D. All right, so this is our plunger, guys, like I said, and this is our ram. So this is our ram and this is our plunger here. All right, so the question is to calculate the force that is going to be exerted by the ram. So we need the force that is going to be on the ram. So we know that the force on the ram is referred to as work done, which is WR there, or you can just have it as the force on the ram, like that. Depends with how you want to write it. This is just one and the same thing. So how are we going to have this, guys? We do not even have the force that is even on the plunger there. We don't have it. All right, these two can this here can give us a relationship. Remember the relationship between the plunger and the ram, that F on the ram, which is, we said we can write it as W, or you can write it as what, as FR. I don't know how you're going to write it. So that is on the ram over the force that we are going to have on the plunger is equivalent to the diameter squared on the ram over the diameter squared on the plunger. But okay, anyways, this we do not have at this moment. This we can create a relation because the relationship is there, so these ones are there. So which means we have to play around to calculate maybe FP so that we can use it to calculate this W. So where are we going to have FP, which is the force on the what, on the plunger? There is a great relationship between the mechanical advantage, because there is mechanical advantage there. So we know that mechanical advantage is equivalent to the force on the plunger over the effort, okay, multiply, because here there is efficiency of 93%, so we are going to multiply by 100 over the efficiency. So that is it, guys, because we've got what, efficiency there. So we can play around this to calculate this FP. So I don't know how you are going to do it, but you can substitute your values, play around with this. Your mechanical advantage in this case is 15, so 15 is equivalent. So remember, we want to calculate FP, which is the force on the plunger. So you've got the effort is 200 multiplied by 100 over the efficiency of 93%, like this. Okay, so we want to remain with this F here. So simply we are going to, or I don't know how you're going to do it. Maybe you're going to multiply everything, or you can simply reduce, or whatever. I don't know the way that you're going to do it. But your FP, if you cross multiply this, you're going to have 15 times 200 times 93. You multiply them this side over, divide by 100, which is going to give you FP. But here you can play any gymnastics that you can do there. You still have to obtain the same answer. So your FP from this information is going to give you 2790 Newton. So we have the force on the plunger from the mechanical advantage and the efficiency. Then it's now easier for us to calculate the work done, which is the force that is on the ram, because we've got this formula that we wrote here. We can transpose, or we can manipulate by just multiplying by FP both sides, which means we have the force that is on the ram, which is going to be d squared over d squared. So there is a relationship that we wrote, that this d, the small d, is 0.1 d squared. So which means we shall write our answer in terms of d squared. So it is going to be d squared over, whenever you see this d, we see 0.1 d. So it is going to be 0.1 d like this, but squared. All right, times the FP, which is the force on the plunger, which is the one that we calculated, 2790. All right, so now what is the force on the ram, which is all done. So as you can see, we're going to have d squared like this over 0.1 squared times d squared. This square is going to affect 0.1 and d squared times 2790. So definitely these two can cancel. So you are going to be left with 2 7s over 0.1 squared. So which means our W is going to be 2790 over, because this is like over 1. So it's this one times this one, because it is cancelled. So it's this times 1 and 1 times this, which is 0.1 squared. So 1 times 0.1 squared, it's 0.1 squared, like that, which you can use your calculator. So this is the force that we need on the ram. So that's it, guys. So we can be very glad that we have this answer now, which is 279,000 Newton. So that's it, guys, which you can convert to kilonewton, which is 279 kilonewton. So as you know these formulas, or as you play around formulas, then engineering science can tend to be a nice subject for you. But if you refuse now to work with formulas, then it's going to be something that is difficult for us. But anyways, guys, let's move on to question 5.4. We are given the plunger of a 3-cylinder pump. Take note, it's a 3-cylinder pump. So you've got C there, which is the number of cylinders, which is 5.4, which is 3. And there's a diameter of 90 millimeters and a stroke length. So take note, diameter, that's a plunger here. So the plunger, okay, let's just take this as our diameter, which is 90 millimeters. Just convert this to meters, divide by 1000, which is 0.09 meters. This one is direct. Then we have got H, which is the stroke length, 590 millimeters divided by 1000, which is 0.59. So we've got 0.59 meters. All right, then we are given that this is what we have. Diameter, did I put, okay, diameter, stroke length, C, and what else? The crankshaft speed. All right, we are given the crankshaft speed of 200 revs per minute. So we are given our N, which is equivalent to 240 revs per minute. So to find N, we divide this by 60, which is going to be revs per second now. So if we divide by 60, that's going to be 4 revs per second. So we now have N in place of N. All right, anyways, calculate the quantity of water. Quantity of water, that is volume. So you need volume of water, but delivered in liters. So you know that volume, we are going to have our volume in cubic meters because we have got meters here per second. Then you convert to liters per second now. All right, if the slip is 1.8%, okay, why given slip? We know that from slip you can find efficiency, because efficiency is equivalent to 100% minus the slip percentage, which is 100%, minus the slip percentage, which is 1, where did I, okay, it's here, minus 1.8. that's your slip percentage. So you multiply by we should subtract 1.8. Note that you multiply, you subtract 1.8, which is going to give us 98.2%. 98.2%. okay, or as a decimal, it's just, or you can just write as a decimal without percentage, which is 0.928, 982, not 0.982 as a decimal, or you can leave it as a percentage. But when you remove percentage, remember you're going to have that over 100. Okay, anyways, that's it. So what do we have here, guys? We want to calculate the quantity of which is the volume. So therefore, where are we going to have our volume? So our volume is going to be like this. The volume per stroke, we need the volume. Okay, we are going to have it like this. Let's take our information here. We are going to have this as the volume, which is equivalent to the volume of the stroke. Then we multiply by, there's a lot of things that we have to include here. So what do we have to include? We have to multiply by the efficiency. There's efficiency, remember our efficiency here, which is 98.12. Say it is 98.2, which gave us 0.982. So we've got efficiency. All right, we also have the speed, so we have to multiply also by the speed. Okay, what else do we have? We have got the number of cylinders, which is C. Yeah, multiply by C. So yeah, that's gonna be our volume there. All right, let's see if we're going to win. We know that this volume of the stroke is the one that we know that it's pi d squared over 4 times h, which is the stroke length. Okay, so this is it here. So it's pi d squared, which is your d, is 0.09. So it's pi times 0.09 squared over 4 times h. This h is for the stroke length, which is 0.59. 0.59 times the efficiency. So the efficiency, which is this over 100, or you can just take this as a decimal, which is 0.982 times n, which is revs per second. Remember our n in revs per second, we calculated this and we got 4 times the number of the cylinder that we are working with. It's a 3 cylinder, so we are going to multiply by 3. Okay, so make sure that everything is actually there. All right, then you are going to obtain this from our calculator, 0.04423, something like that, which is in cubic meters per second. But we are told to give this in liters per second. So, and we know the relationship that in a cubic meter we have got 1000 liters, which is 1 kiloliter. 1 kiloliter, like that. So we are going to multiply by 1000, so that this will be in liters, which is going to give us that's 44.23, 44.230, something like that. 0.23, yeah, that's this zero, it does not matter, in liters per second. So this is going to be liter per second, or L per second. That's our volume now. Okay, I don't know, guys, if it was clear, but that's what we had. And as you can see, it's a matter of play around with the questions and so forth. And 5.5, we are given a bore pumps water from a depth of 65 meters at a rate. We are given the, so let's take the height. We have got the height here of 65 meters, and it's pumping this, or it's doing this at 320 liters per minute. So each minute it has to cover 320 liters. So we know the relationship that in a cubic meter, like we said, it's gonna be, in a cubic meter we said we have got 1000 liters, and this is pumping what are we having? Yeah, okay, 320 liters. So now we have got liters, we have to divide by 1000. So it's gonna be 320 liters. We want to convert to cubic meters, so you divide by 1000. So 320 divided by 1000, which is going to be 0.32, which is in cubic meters per what, per minute. But this must be in per second, so this is per minute, and per second it's gonna be 0.32 over 60 now per second, which is going to give us 5.333 times 10 to the power minus 3. So that's our volume there, which is in cubic meters per second. All right, anyways, let's see what we need here. We are given the installation efficiency of the pump is 75%. That's the efficiency. It's 75% there, then, which is 0.75. Calculate or determine the power of the driving pump of the electric motor. So we need the power there, and we know that power is equivalent to, because if you have got volume like this, power is equivalent to, this is power, pressure times volume. So this is pressure times volume. But why are we talking of pressure here? Do we have volume? Yes, volume is there, but we do not have pressure. So we have to calculate that. And we know that pressure is equivalent to rho GH, which is density times. So we have to find the density for water. And the density for water is actually there, because the density of water we are given is 1000 there, kg per cubic meter. So we've got 1000 times 9.8 times the height where this water was being pumped. The height was 65 meters, I think we had this 65. So we are going to obtain a pressure in this case, which is 6 637,000 pascals. Remember, pressure is measured in pascals. Now that we have the pressure, we can calculate the power, because we said power is pressure times volume. So power is pressure 637,000 times the volume, the one that we calculated. Okay, here, this one, 5,333 times 10 to the power minus 3. Yeah, that's what we had. So let's just combine this from our calculator, guys. Then we are going to have, and also which power are we calculating here? This is the power of the driving pump. So we need the input power. So guys, we have got a lot here. So we need the input power actually, which we do not have. So this is our output power. Yep, P out. All right. So okay. Anyways, let's find our P out first, and I'll tell you. I'm gonna show you what you're going to do here. This is what you're going to obtain in watts, or you can convert to kilowatts, depend with what you want. So if this be our output power, this one, and as we need the input power, while least we have the efficiency. So what does that tell us? We can play around with efficiency, because we know that efficiency is equivalent to output power over input power times 100% if you want. So I'm going to use as a decimal, so there's no need for me to use 100%. So cross multiply efficiency times P in is equal to P out, divide by P in divide by efficiency there. So our P in is going to be P out, which is this one, 3397,121 over efficiency. So I'm going to use efficiency as a decimal, because I didn't use 100% on this formula. I didn't use 100%, so I'm going to substitute this as a decimal. If you use 100%, then you don't use that one. You're going to use the actual value. All right, so that's our P in there, which is going to be 4,5. So you're going to obtain 4,529,4946, which is 495 if you round off properly, which is watts. So that's your P in, or you can even write this in kilowatts, which is 4, there, something like that, 4,529 kilowatts. That is if you want, but actually the answer was just direct. So writing in kilowatts or this is it's something else. But anyways, then on 6.1 you're asked to state the Hooke's law. So from your calculations from our definitions, this is what we have. Hooke's law states that for an elastic object, the strain is directly proportional to the stress causing it. And so man, I don't know which one that you had, which definition did you have there. Then on this question we are given that the figure below shows the middle steel bar, which is actually loaded by means of a tensile load, so that the maximum induced stress is 120 megapascal. So this is the one that is given the force of 120 megapascal. All right, so and the Young's modulus is 200 gigapascal there, which is calculate the total length, the total change in length. So that's the question, to calculate the total change in length. So we are given the distance. This is the diameters, the diameter, the length. So this is the original length, the diameter, original length, diameter. Okay, so let's just list our information here. We want the total change in length, which is xt, which is x total. All right, so what are we given here? From the first part, we are given from this steel, this is a length of 200 millimeters, which is in meters, divide by 1000, which is going to give us 0.2. So you've got the original length of 0.2 meters and a diameter. So this is your diameter, 50 millimeters, divide by 2. 50 millimeter divided by 1000, so to meters divided by 1000, sorry, which is 0.05 meters. Then we move to the second length, which is 175 millimeters, which is divided by 1000 is going to be 0.175 in meters. Then our D2, we do the same, 40 divided by 1000, 0.04 meters. We move on to the third length, which is 150 divided by, which is 0.15 meters, and D3 the same, which is going to be 0.03 meters. Okay, and we are given the force here of 120 and the Young's modulus. So the force in this case is 120 megapascals, which is 120 times 10 to the power 6 newtons or pascals. The stress, this is our stress, sorry, this is our stress, not the force, guys. Okay, which is in pascals. Then our E, which is 120, that is giga, which is times 10 to the power 9 pascals. All right, so I don't know how I was actually reading this question, but anyways, that's it. So the question needs us to calculate the total change in length. I was looking for the question which is already there. So what is going to be the total change in length? So I'm going to use this formula. I don't know if guys you had came across this one, that xt, which is x total, is gonna be 4f over the stress there, which is pi e into L1 over D1 squared. So you have to memorize this formula if you want it to be easier for you. D2 squared L3 over D3. So as you can see, it corresponds to length and its diameter, length and its diameter. So what you need is to know only this part here is the one that you need to know. So it's going to be 4 times the stress which we are given, which is 120, times 10 to the exponent of 6, which is the force there, over pi times E, which is 200 times 10 to the exponent of 9. Okay, everything into now you have to substitute there. So that one, your information is there. L1 over its diameter squared, 0.2 over this. So it's 0.2 over 0.05 squared plus L2 over D2 squared. So it's this one. So it's just a matter of substitution, 0.175 over D squared, which is 0.04 squared, plus L3 over D3. So it's this over this, which is 0.15 over the diameter squared, 0.03 squared. So it's a matter of the formula, guys. You must know that formula, and you can actually substitute everything, which is going to be 0.2719, something like that, which is 719, which is going to be 2. So this is our x total in meters. All right, so converting to millimeters, if you want, you multiply by 1000, which is going to be 272 millimeters. So it depends with how you wanted to present your answer, in meters, millimeters, or I don't know. But that's what we had from this question. Then that's it. On 6.3, we are now given, during a tensile test on a round bar 25 millimeters in diameter, we are given a load of 80 kN causes an extension of 0.2. So these are actually taking out the information. I think that's best here. So you must make sure that the information is clearly given. So that's 6.3. And what we have got a round bar which is 25 millimeters in diameter. So we've got diameter here, which is divided by 1000, is going to be 0.025 meters. And a load of 80 kilonewton causes an extension. So we've given a load, which is the force there, of 80 kilonewton. That's 80 kilo. Kilo means 1000. So multiply by 1000, which is going to be 80,000 newton, like that. Okay, then an extension is going to cause an extension of 0.2 millimeters. 0.2 millimeters divided by 1000. So that's an extension, which is x, which is 0,2. If you divide by 1000, this is gonna give you something like 2 times 10 to the power minus 4 meters. All right. Then if the initial length, which is the original length, is 250 millimeters, so that's your L, which is divided by that is gonna, the 1000 is gonna give you 0,25 meters. So that's what we had from this information. The question on 6.1 is to calculate the stress. So what is going to be the stress there? So our stress, that's stress, we know that stress is force over area. So it's force over area. Do we have the force? Yes, the force is there, but we do not have the area. But we know that area is equivalent to pi d squared over 4. So this is going to be force over pi d squared over 4 like this. Okay, so our force in this case, that's 80,000. That's 80,000 over the area, which is pi times d. That's 0. This diameter here, 0.025 squared over 4 like this. All right, so that's what you're going to have in this case. If you are to simplify, make sure that this is in a bracket, this is one thing in a bracket, including this 4. So you shall obtain your stress, which is in this case, that's this value 1,629,744, no, it's 7,466 1.7, which is in Pascal. So you can convert maybe to megapascals, which is 3 here. That's 6. Remember, mega means 6 digits after the comma, so it's gonna be comma here, which is 162,97, and this is gonna change to 5 to 3 decimal places, which is now in megapascals. All right, so at least it can make sense if we do it this way. Anyways, that's what we had for them from this information. And let's see another part where we want to calculate the strain. So remember, the strain, that's gonna be the change in length over the original length. So that's 6.32. That's our strain, which is the change in length over the original length. So of which, from this information we have it. The change in length is actually there. The original length is there. So it's 2 times 10 to the exponent of -4 over the original length, which is 0,25 meters. All right. So that's it. And it's going to give you 8 times 10 to the exponent of -4. So that's it. And you can just leave it like that. No need for you to have any further adjustment there. Then on 6.33, we are now asked to calculate the Young's modulus. So the Young's modulus, we know that that one is E. And E, how can we calculate E if we have got the stress and we also have the strain? Our E is going to be the stress over the strain. So this is stress over strain. So we're just substituting our stress and our strain there, which is the values that we obtained. And now thrown out this, but our stress was something like 162, something like that. Okay, so I'm gonna just write it down. That was 162,975. We said that one was now megapascals, so it's gonna be times 10 to the exponent of 6 over the strain, which is 8 times 10 to the power minus 4. 8 times 10 to the exponent of -4. So you shall have this from your calculator to the exponent of 11, which is 2,037, something like that, which is times 10 to the exponent of 11 in Pascal. So you can maybe convert to megapascal, or you can just move one comma, which is 0,2084, which will be times 10 to the power 12, which is gigapascal. So here you can convert the gigapascals to mega, but as long this one is there on your answer, this is what is important, that you obtain it. Or you can even leave it at this stage if you don't know how to convert to mega or to gigapascal, so that you don't lose your final answer if you had done it in a correct way, just by converting to gigapascal or to megapascal. you lose your answer by that. So you can leave it like that. Define Pascal. So in this case, as you can see, guys, this was 2 questions on hydraulics. I don't know, but that's what we had. So Pascal's law, just to define, so you know that Pascal is all about the pressure. That is the one that we have that is gonna be maintained or transmitted with same intensity throughout the liquid in all directions. So that's all about Pascal's law. It's all about the pressure. Okay, the piston in a single acting, so this is a single acting water pump, is a diameter and delivery stroke and must be pumped to a vertical height of 20 meters. So there are 2 things that we have, the stroke length and another height that we are going to use. So okay, anyways, I'm going to use it like this. We have a diameter of the piston, which is 100 millimeters. So that's going to be divided by 1000, which is 0.1 meters, and the stroke length, which is 80 millimeters. So divide by 1000 again, which is 0.8 meters. Then we have got the vertical height that the water is to be pumped at, which is going to be h. I'm going to use this as h, which is 20 meters. All right, so this is our stroke length. All right, so the question is to calculate the volume of water being pumped per delivery stroke, which means you are working with the stroke here, and that's the volume for the stroke here, which is equivalent to area times the stroke length, which is area, we said is pi d. So as you can see, guys, it's a matter of repetition here, which is pi times d 0.1 squared over 4 times the stroke length, which is 0.8. So you are going, guys, this is 80 millimeters there. All right, so we've got 80 millimeters, which is 0.08. 0.08. That's all. Divide by 1000. That's 0.08, guys. If I'm not mistaken, that's 1, 2, 3. I'm not having my calculator here. Wait, there, put 0.08. Okay, let me just find my calculator. Okay, that's 0.08. Okay, I just got this calculator. This is 0.08, not 0.8. I hope someone saw this. All right, anyways, that's what we had, and we have to multiply, which is going to give us 6,2831, something like that, times 10 to the power minus 4 times 10 to the power minus 4. This is 6383. Yeah, times 10 to the power minus 4, because it was 831, something like that, which is in cubic meters. So that's our volume. Do we have anything that we can do? There's nothing, because this is the volume for the stroke. So just leave it at this moment here. So that's what we had, and now we are, so which means we have nothing to do with this height of 20 in this case. Okay, that's it. We do not have anything to do with it. Anyways, the mass of the water pumped per delivery stroke, what is going to be the mass? So you know that mass can be obtained from this formula. Actually, density is mass over volume. So mass, we just multiply density and volume. Volume is mass over that density. So you can multiply. Remember, guys, that density is measured like kgs per cubic meters, like that. So which means it's gonna be mass over volume. So which is the density of water, and in this case you are referring to water. That's 1000 kilojoules per cubic meter there. So it's gonna be 1000 times the volume. Yes, we obtained it here. So we have the volume. So let's go back and trace our answer. That's our volume here. So guys, we've got a lot, and I'm so tired now. Anyways, that's it here, which is gonna be 0.6283 something, yeah, which is in kgs. That's your mass. So anyways, that's what we had. And 7.3, we now have the following data, which is the data refer to the single acting hydraulic press. That's a single acting hydraulic press. You're given the plunger diameter, which is just maybe small letter d, which is divided by 1000, just like that 8. You see that mistake was going to cost us a lot. Anyways, this is going to be 0.08, just like what we obtained here. And the plunger stroke, which is 0.12 divided by 1000. Then the ram, so on the ram we've got 0.3 meters. And the slip, remember I told you about the slip, that whenever you're given the slip there, it helps you to calculate efficiency, because it's going to be 100% minus the slip, which is 5%. So we are going to have 95% efficiency, which is 0.95 as a decimal. All right, so the question is to calculate the actual volume of the liquid delivered to the ram per stroke. All right, what is going to be actual volume of the liquid delivered to the ram per stroke? All right, that's our actual volume. We shall have this as remember we've got it was supposed to be area times the height. That is we're supposed to be from the plunger to the ram, because it's delivered to the ram from where? From the plunger. All right, so that's gonna be area times height, and we've got efficiency because we now calculated that. So we multiply by efficiency, of which I told you that area is pi d squared over 4. So it's gonna be pi times d squared, which is our diameter here, because we are taking from the plunger to the ram. So we're going to use the diameter of what? Of plunger, which is 0.08. 0.08 squared over 4 times the height, which is on the plunger here, 0.12 times the efficiency, which is 95%, or 0.95, like that. So that's our volume, our actual volume in actual sense. This is the actual volume, which is 5,7302, something like that, which is 7 there, like that, times 10 to the exponent of -4 in cubic meters. So that's what you're going to have as your actual volume in cubic meters. Then on 7.32 is now the distance moved by the ram after 5 pumping strokes. Of take note, after 5 pumping strokes. So which means there is something there that we are supposed to do with our pumping strokes here. So remember actually that okay, the number of pumping strokes in this case is 5. So the volume that we shall have is supposed to be the same. So we are going to take area in this case. I don't know how we are going to put it in a nicer way, because we have these guys. We've got 5 pumping strokes on the stroke, or 5 pumping strokes, which is affecting the plunger in this case. But on the plunger, we've got the volume, which is the one that we obtained. So we are going to say that volume, which is the actual volume, times the number of the pumping strokes, which is because these ones, they affect the plunger. So that's why I'm applying to the volume. I'm multiplying to the volume, is equivalent to the area that is going to affect the here. Since we are working with the volume here, you're supposed to work with volume. So volume, remember I told you that it's area times the height. So you're going to multiply by the distance, which is that on the plunger, on the ram. So this one is for the ram, this one is for the plunger. Take note. So this area, yes, it's pi d squared over 4, but this time you are using the diameter of where? Of the ram, because we are talking of the volume on the ram, the area that is going to be there. So that means we can be able to transpose or to manipulate this formula here like this, so that we can find our H. So our H is going to be the volume, actual volume, times the number of pumping strokes times the area, which is pi d squared over 4 that's what we have. So we're gonna substitute the volume. We have it. This is the volume that we calculated at first place, which is that one of which was transmitted there, which is this 5 point what is that we have there, 5.73 times 10 to the exponent of -4 times the number of pumping strokes, which is 5, everything over the area, which is pi times, like I said, we are working with the ram. So what's the diameter on the ram? We say the diameter on the ram here is 0.3, so it's gonna be 0.3 squared, everything over 4, like this. So you have to close the bracket. So make sure you put this on top, then you close bracket, so that your answer is going to be an exact value. And this h here, which is the distance traveled, is going to be 0.04053, something like that, which is 0.041 in meters. Okay, so that's what you're going to obtain there. So as we can see, guys, that was the question, which is 7.3, and it was actually carrying 4 marks to make a total of 15 marks on question 7, and making a total of 100 from this question paper that we had. So that's it, guys, from the question paper, which was actually written in July 2022 for engineering science and 4. So for any part that maybe we did improper substitutions and later on obtained wrong values, let's know on the comment section so that we can work on it. And also, like I said, we shall come back again working with other methods, so forth. But for the meantime, yes, just for you to know what was actually happening in that exam and what we had. So that's it, guys, from Mason African Motives, working on engineering science and 4, till we meet again.